Hello and welcome to the video lecture on carbohydrates. In this part we will discuss the chemistry of disaccharide, particularly the molecule of sucrose, which is the ordinary table sugar, and also a little bit about polysaccharides. So disaccharide, as the name suggests, it's a carbohydrate molecule which on hydrolysis yields two molecules of monosaccharides. When you make a disaccharide, you react basically two monosaccharides, and the two monosaccharides are connected to each other via a condensation reaction. Between two monosaccharides, you are going to form a glycosidic bond, and that is achieved by placing a leaving group at the anomeric carbon of one particular monosaccharide, which is known as the glycosyl donor, and then reacting that glycosyl donor with a free hydroxyl group of another monosaccharide, which is known as the glycosyl acceptor, and this reaction is known as a glycosylation reaction. It is to be noted that the term glycosyl, it is defined as the structure that is obtained by removing the hydroxy group of the hemiacetal function of a monosaccharide. Suppose if X is equal to OH, then the rest part, this is the hemiacetal carbon, the anomeric carbon, and the rest part of the molecule barring the OH, that would be known as the glycosyl group. So this monosaccharide in this condensation reaction offers the glycosyl group, therefore it is known as the glycosyl donor, and the molecule which accepts the glycosyl group through one of its free hydroxyls is known as the glycosyl acceptor. See how you have protected the other OH groups of this glycosyl donor, and you have a X, particularly a good leaving group such as a bromine or a fluorine or a alkyl thiol group that is present in the anomeric carbon. And from the glycosyl acceptor, you are giving a free hydroxyl which is reacting in the glycosylation reaction, so that you may make a glycosyl bond here and you form a disaccharide. So apparently the reaction does not look very complicated, but it's not as simple as it looks. There are a certain number of difficulties that are associated with it. First of all, the glycosylation reaction, the reaction has to be strictly anhydrous, because this is a very labile bond, because if you make X leave as X minus, the carbocation which is generated is resonance stabilized, and therefore it's oxocarbenium ion, and therefore is extremely susceptible to hydrolysis. So presence of even small amount of water will hydrolyze the glycosyl donor, and the water will act as a competing nucleophile, and it will compete successfully with the glycosyl acceptor's free hydroxyl group. The second point is that you need to worry about the regioselectivity. So in glycosyl acceptor, you must not have any regioselectivity issue. If there are multiple free OH groups, then all of those has the potential to react with this glycosyl donor, and therefore you will end up with a mixture of regioisomeric disaccharides. That is what you don't want, and therefore preferably you should have only one free hydroxyl here, which will unambiguously react with the glycosyl donor. Third point is stereoselectivity, because you know that at this anomeric carbon the linkage with this glycosyl acceptor could be of two types. One is the alpha linkage and the other is the beta linkage. So there is always the interglycosidic linkage being alpha or beta. There is this issue that you have to think about. And fourth point is that here your secondary hydroxyl, or maybe at best a primary hydroxyl, is acting as a nucleophile. In general, alcohols are not particularly good nucleophiles, especially if you have hindered secondary alcohols or partially protected glycosyl acceptors where there is bulky protecting groups present. So they do not react very well, and therefore they react the reaction rate is slow and the yield is not great. Therefore, this apparently simple reaction is associated with a number of difficulties which you need to overcome, and there have been many efforts directed towards developing synthetically efficient glycosylation reactions, which will first lead to disaccharides and then to oligosaccharides. One of the example I have illustrated here, we have taken a glucopyranosyl unit where at the anomeric carbon you have a leaving group bromine placed at the alpha position. This is a 2,3,4,6 tetra O acetyl. See, I have to protect all these acetyl, all these hydroxyls, because otherwise a self condensation reaction will take place. I don't want that. This is my glycosyl donor. My glycosyl acceptor is a galactose derivative where I have protected the C1, C2, C3 and C4 hydroxyls via diacetonide derivative. It is only the C6 primary hydroxyl which is free, and that is what will react with this at this anomeric carbon of the glycosyl donor. And to facilitate the reaction, we have used a silver triplet, and silver plus will assist in the departure of the bromide. Molecular sieve is used as a catalyst, and in anhydrous dichloromethane we are doing the reaction. The anion associated with silver is triplet, that is CF3SO3 minus, which is resonance stabilized and also enjoys the minus I inductive electron withdrawal of the CF3 group. Therefore, its nucleophilicity is very less, and therefore it does not act as a competing nucleophile at all. Therefore, we can successfully combine these two to get this particular compound, and here the linkage that we observe is beta, although we have started from the alpha bromide, but the linkage that is established, that is the beta linkage. Okay, so let's now move to our common disaccharide that we know, that is the table sugar sucrose. Ordinary table sugar is a disaccharide which is known as sucrose. It is the most widely occurring disaccharide found in all photosynthetic plants, and it is obtained commercially from sugarcane or sugar beets. The structure of sucrose in Fischer projection formula, it looks like this, and if you draw the Haworth projection formula, then it looks like this. And if you draw the Haworth projection formula in such a way so that the two glucose, the two carbomonosaccharide units are right above one another, one above the other, not like this, then you can understand very clearly that this is a glucopyranose unit. The linkage is alpha, and this is a fructofuranose unit where the linkage is beta. So it is the alpha anomer of the D-glucopyranose and the beta anomer of the D-fructofuranose, and when you combine these two, you eliminate a molecule of water so that both the hemiacetal linkages are converted to the acetal. But in general, the molecule is not drawn in this way, it is drawn in this way either or in this way. From this you can understand that this is the glucopyranosyl and this is the alpha, and this is the fructofuranosyl and that is the beta, because your configurational carbon, DL configurational carbon is on that side and your OH is on the opposite side. So in the fructose it must be the beta anomer, and it is also coming from the fructofuranose, and on this side you have the oxygen, configurational oxygen at C5, that is on the right side. So it's a D sugar, it's a D glucose, and you also have the anomeric OH on that side, on the same side, on the right side. Therefore it's the alpha anomer. So how do I get this here, or how have I drawn this here? It is actually, this is the beta anomer of the fructofuranose form. So see, the oxygen is projecting upwards, therefore it is the beta anomer. And if you flip it upside down, if you flip this thing upside down, then this C1 will come here and the C6 will go here. So C1 is here, and now the oxygen is on the on projecting below, but that does not mean that it is the alpha anomer, because when we draw the sugars in this way, we have to maintain two conditions. One condition is that the anomeric carbon will be on the right hand side and the ring oxygen will be away from us, just as we have drawn here. Anomeric carbon is on the right hand side, ring oxygen is away from us, so this is projecting below, so that must be the alpha anomer. However, in this scenario, the anomeric carbon is C2 and that is not on the right hand side. We have rotated the molecule and therefore it appears at the left hand side, and therefore the oxygen that is projecting below, that must be the beta anomer, not the alpha anomer. So the UPAC name of sucrose is, you can think of it as a derivative of glucopyranose, or you can think of it as a derivative of fructofuranose. Accordingly, you can name this molecule as alpha beta D fructofuranosyl D glucopyranoside, or beta alpha D glucopyranosyl D fructofuranoside. In the first case, your parent molecule is alpha D glucopyranose, and because this is a acetal, it will be termed as a pyranoside, and because your substituent at the anomeric carbon is D fructofuranosyl, the linkage of which is beta, the total substituent is therefore named as beta D fructofuranosyl. On the other hand, if you consider it as a derivative of the D fructofuranose, then because it's an acetal, you will call it D fructofuranoside. Because it is beta, you will call beta D fructofuranoside, and at the anomeric carbon C2, you have the alpha D glucopyranosyl substituent, and therefore you will call it beta hyphen bracket alpha hyphen D hyphen glucopyranosyl bracket close hyphen D hyphen fructofuranoside. So pretty formidable name, but if you understand how they are naming it, it's not as scary as it looks. Let's now discuss the evidence or the facts that we have from which we can think about the structure. We already know the structure. If you are comfortable with the Fisher projection formula, then please draw that. If you are comfortable with the Howard projection formula, then please draw that, and make sure that you understand that you can convert this Fisher projection formula into this Howard projection formula by using the LURD trick that we have talked about. So the structure of sucrose was determined following the evidences that we have listed here. The molecular formula was found to be C12H22O11. And it was observed that if you hydrolyze 1 mole of sucrose, then it gives you 1 mole of D plus glucose and 1 mole of D minus fructose. Now, this is a very interesting concept. Sucrose is dextrorotatory and its specific rotation is plus 66.5 degrees. When it is hydrolyzed, it gives you 1 mole of sucrose gives you 1 mole of D minus fructose and 1 mole of D plus glucose. But the dextrorotation of the glucose and the levo-rotation of the fructose molecules, their specific rotations are not the same. D minus fructose has a higher specific rotation, that is minus 92 degree, higher levo-rotation compared to the dextrorotation of the D plus glucose, which is only plus 52.5 degrees. As you know that this is the optimal value for D plus glucose, where alpha and beta anomer has already equilibrated. Similarly for fructose, the rotation, after the rotation, the optimum specific rotation is minus 92 degrees. So you have started from plus 66.5 and then you are ending up with a equimolar mixture of two compounds, one of which specific rotation is minus 92 and the other is obviously plus 52. Because the levo rotation is greater than the dextro rotation, the final reaction mixture will have net negative specific rotation. So the hydrolysis of sucrose, before the hydrolysis you had observed dextro rotation, and during the hydrolysis the rotation changes to the corresponding mixture of 1:1 mixture of glucose and fructose, and the overall rotation becomes levorotatory, and that is why this reaction is known as inversion of cane sugar. Because sucrose is derived from cane sugar, so it is expected that from cane sugar our sucrose will be dextrorotatory, but if I hydrolyze it in dilute HCl medium, obviously the hydrolysis will have to be catalyzed by dilute acid because this is an acetal. Acetals do not cleave under basic medium, you have to use dilute acid. So or you can use the enzyme invertase, which is produced by the Baker's yeast. If you do that, then the dextrorotatory sucrose will be converted into a levorotatory mixture of equimolar mixture of fructose and glucose. But do not confuse this with mutarotation. Mutarotation is something entirely different, where two hemiacetal forms, two anomers equilibrate. Here you are basically doing a chemical reaction, acetal hydrolysis, and in that case you are doing a hemiacetal hydrolysis followed by again hemiacetal ring formation. Here you are doing acid catalyzed acetal hydrolysis to two different monosaccharides. So this is not mutarotation, although the optical rotation or the specific rotation is changing with time, and you can monitor this polarimetrically. And this is one experiment which is done in undergraduate physical chemistry laboratory. By you can measure the rate of the reaction of the cane sugar's inversion. Now, because this is acetal and therefore it is not supposed to mutarotate, it is not supposed to undergo cleavage when you place it in water, or because there is no free hemiacetal OH, and the molecules cannot go to the acyclic hydroxyketo or the ketoaldehyde or the hydroxyaldehyde forms, sucrose is therefore supposed to be a non-reducing sugar, because we know that the capacity of acting as a reducing sugar and the capacity of mutarotation, both of them depends upon the free hydroxyl at the anomeric carbon. But at C2 of the fructose unit and at C1 of the glucose unit, nowhere can we see that there is a free hydroxyl, and both of these linkages are like acetals, and therefore it gives negative tests with Benedict's and Tollens solutions. Sucrose also does not form any osazone because there is no free aldehyde or a keto group available, and it does not undergo mutarotation. All of these point to the fact or expectation that the anomeric OH of the glucose is linked with the anomeric OH of the anomeric OH of the fructose unit. So basically you are eliminating a molecule of water from the C1 hydroxyl and the C2 hydroxyl of the glucose and fructose respectively. Sucrose is hydrolyzed by alpha glucosidase enzyme, which is obtained from yeast, but it is not hydrolyzed by beta glucosidase. Now glucosidases are the glycosidic link, they are capable of cleaving the glycosidic linkages, such as the glycosidic linkage here or here. Now glucosidase cleave the glycosidic linkage where one molecule, one part of the glycosidic linkage is made up with glucose. And specifically if you use alpha glucosidase, then only if the glycosidic linkage from the part of glucose is alpha, then it is cleaved, otherwise it is not cleaved. And if you use beta glucosidase and then you observe hydrolysis, then you must admit that the glycosidic linkage for that substrate on the part of the glucose unit has to be beta. Our observation is that sucrose undergoes hydrolytic cleavage catalyzed by alpha glucosidase and not beta glucosidase. Therefore we must concur that the C1 linkage or the anomeric linkage, the glycosidic linkage at the glucose anomeric carbon will have to be alpha and not beta. And sucrose is also found to be hydrolyzed by sucrase, that is an enzyme which is known to hydrolyze beta anomers of fructofuranosides. So only the beta anomers of the fructofuranose, that is hydrolyzed, or I should say fructofuranosides, that is hydrolyzed by the sucrase. So again, just like you have admitted that this must be alpha linkage, you have to admit that the C2 linkage or the C2-glycosidic bond from the sucrose part, from the fructose part will have to be beta. This indicates the beta configuration at the fructoside portion and alpha configuration at the glucoside portion, because enzymes are extremely specific. And now about the ring size. How do I know that fructose is furanoside and the glucose is pyranoside? For that, they have done a lot of classical chemistry, some of which we have illustrated here. So all you do first is you methylate everything. So there is 1, 2, 3, 4, 5, 6, 7, 8 free hydroxyl groups that is present in the sucrose molecule. So you methylate with dimethyl sulfate, and prior to that you deprotonate everything with strong base sodium hydride. And now everything is ether except for this linkage, and except for that linkage, and except for that linkage, because those are acetal linkages. So that linkage is basically acetal. So you hydrolyze. Once you hydrolyze, the acetals go, and these things becomes a hemiacetal. So this is a hemiacetal at C2, this is a hemiacetal at C1. This is the anomeric carbon of the glucopyranose form, and this is the anomeric carbon of the fructofuranose form. Obviously, this is a 2,3,4,6 tetraomethyl glucose hemiacetal form, and it can exist in the open chain hydroxyaldehyde form, where the C5OH is free and you have CHO at the C1. If you impart hot nitric acid for oxidation purpose on this molecule, then the CHO will be immediately oxidized to CO2H, and this free secondary hydroxyl will become keto. And if you do the reaction even under harsher condition, then the keto acid will undergo cleavage. When the cleavage is between the C5 C6, we know that when ketones are oxidized under forcing conditions, they afford carboxylic acids with lesser number of carbon atoms, because carbon-carbon bond cleavage takes place. So here, if the C5 C6 bond is cleaved, then I get this xyluric acid, and it is actually 2,3,4-triomethyl D-xyluric acid. And also, if the cleavage is between this C5 and this C4, then this C4 will become carboxylic acid, and I will get 2,3-diomethyl L-tartaric acid. This outcome is only possible if my C5OH was oxidized to carbonyl, because this molecule is coming from the cleavage of C5C6, that molecule is coming from the cleavage of the C5C4, which means that prior to HNO3 oxidation, the secondary hydroxyl group was at the C5, which means that it is the C5OH which was forming the hemiacetal ring with the CHO at C1, and therefore it must have been a 6-membered ring, and therefore we can safely conclude that it is the glucopyranose form which is present in our sucrose, hydrolyzing which we have done all these reactions. Doing the same reaction on the fructose unit, which was obtained by the hydrolysis of the acetal linkage of the methylated derivatives, then we can see it is the C1 OH which is protected as OMe. The carbonyl is at the C2, and it is the C5OH which is free. Do the HNO3 oxidation again, and you get carbonyl here at the C5, and further oxidation will cleave that bond and will also cleave that bond, and therefore it is the C1C2 cleavage and it is the C5C6 cleavage from which we will get 2,3-diomethyl D-tartaric acid. And that is only possible if the C5OH was free, which means it is the C5OH which is connected to the carbonyl at C2. That means it is a 5-membered ring. That means it is a fructofuranose form which is present in sucrose. This is a very elegant piece of experiment from which you can determine the ring size of the two monosaccharide units present in the sucrose. Finally, this is again the same thing I have written, but this time I have used color codes so that you may find it easier to understand, and that's basically telling you how to apply the LAR trick so that you can have a better understanding of how to construct this Haworth projection formula from the Fisher projection formula. And finally, we talk about a little bit of polysaccharides. Polysaccharides are long chain carbohydrates where many monosaccharide units are connected to each other. One such polysaccharide is starch, out of which two components are very much identifiable. One is the amylose, the other is the amylopectin. As you can see, amylose is the straight chain one, where amylopectin is basically branched one. Where amylose, you have like the alpha anomer of D-glucopyranose combining with the C4OH of another alpha D-glucopyranose, and that chain propagates forming a polymer, so that you have amylose chains, long chains of amylose. On the other hand, if the alpha anomer of D-glucopyranose, such a amylose chain, is forming a linkage, a cross link with the C6OH of another amylose chain, then it is called the amylopectin. Now, amylose and amylopectin is totally insoluble in water, whereas amylose forms a colloidal solution in hot water, and it forms a beautiful blue-black colored complex with iodine. Iodine is normally not very soluble in water, and it is solubilized in water by mixing it with potassium iodide, where I3 minus ion is generated. And this I3 minus ion, where 3 iodine atoms are linearly placed, this cylinder of a circular cylinder or a helical cylinder obtained by the amylose chain can perfectly encapsulate this I3 minus ion, this polyiodide ion, and that complex is characterized by its typical blue-black color. So in titrations using iodide, iodine, iodimetry and iodometry, we use the starch as an indicator, whereby the presence of free iodine can be detected by the blue-black color of when it is complexed with the starch indicator. So there are many other polysaccharides which we do not have the option or the scope to go into details of, but it is in fact a world of fascinating structural chemistry. Glycochemistry by itself is a very hot and very happening field. We have only managed to scratch the surface of it, but I certainly hope that the toolbox that we have prepared here will be of some help and propel some of you who will end up doing sugar chemistry in some way. So I thank you for your patience, and I will be seeing you in the next one.